A warm welcome to the lecture on the subject of wavelets and multirate digital signal processing. We had raised a few questions in the previous lecture, which we set out to answer in this lecture. The questions pertain to the fact that we were building more than one multi-resolution analysis. And specifically the question was, what are we looking for when we go from one multi-resolution analysis to the other? Why can't we be content with the HAR multi-resolution analysis? We have been singing the praises of the HAR multi-resolution analysis so frequently in some of the previous lectures. We have been saying that it tells us most of the things that a multi-resolution analysis does. Why then should we look for others? What is inadequate in the HAR? Well, if you remember, when we began this course, we set out to do something which a basic course on signal theory or signals and systems does not, namely look at two domains simultaneously. We have been trying to do this for a while. So, when we took the HAR, we did at some point talk about the filtering aspect of it. We also talked about the ideal to which we strive in the filter bank. And if you recall, that ideal had to do with the frequency domain, not the time domain. So, somewhere we have not been giving as much importance to the other domain, so to speak, as we should. We have been working in the natural domain of time, but we have not quite been doing justice to the frequency domain. When we take a HAR multi-resolution analysis, what does it do in the frequency domain? We have not quite understood this as yet. And the first thing that we would like to do is to answer this question. What does the HAR multi-resolution analysis do in the frequency domain? And then, how do these filter banks that comprise the HAR build up to that frequency domain behavior? So, let us set out first to answer a more basic question. What is the Fourier transform of the scaling function and the wavelet function in the HAR multi-resolution analysis? So, we shall call today's lecture a joint perspective, time and frequency. And we shall set out first to look at the Fourier transform of phi t and psi t in HAR. So, the HAR MRE. Let us begin with the phi t and let us look at its Fourier transform. Remember how phi t looked. This was phi t. Let us obtain its Fourier transform. We shall use this notation for the Fourier transform, a cap on top and capital omega to denote the angular frequency, analog angular frequency. Radian or angular frequency. And this is easy to calculate. Well, I am saying 0 to 1, actually I should write minus, if you like, I can write minus infinity to plus infinity, but the non-zero part is only between 0 and 1. So, it is also all right to write between 0 and 1 only for this specific function, and this is of course equal to integral 0 to 1 e raised to the power minus j omega t dt, which evaluates to e raised to the power minus j omega t by minus j omega from 0 to 1, and that is 1 minus e raised to the power minus j omega by j omega. And we can simplify this. We can take an e raised to the power minus j omega by 2 common in the numerator. And that is easy to interpret. In fact, if you wish, we can even make this by j omega, all right, 2, and then this becomes e raised to the power minus j omega by 2. If I take the 2 j and this together, I get sin omega by 2 there and omega by 2 here. So, this is the Fourier transform. Now, let us look at the magnitude of this Fourier transform. So, in fact, I could straight away sketch this. It is essentially the magnitude of sin omega by 2 by omega by 2. A sketch would look like this. This is a very familiar function to most electrical engineers. We call it the so called sinc function, the sinc pattern. People have different names for it. They call it the sampling function, the sinc function, and whatever other names. Anyway, this is the point where omega by 2 is equal to pi or omega is 2 pi. And this of course, is the point where omega is 4 pi, and this where it is minus 2 pi, this where it is minus 4 pi, and so on and so forth. At this point, the magnitude takes the value 1. In fact, recall that the magnitude of the Fourier transform, in fact, the value of the Fourier transform at omega equal to 0 is indicative of the area under phi t. So, the integral of phi t over all t. Anyway, so much so for the magnitude. And now, we know what to do when we compress and expand. Let us look in general at the Fourier transform of phi 2 t minus m. So, we should interpret that. You know, we are talking about dyadic dilates and translates. So, let us consider phi, in fact 2 raised to the power of m t minus n, if you please, for m and n belonging to the set of integers. Now, you will recall that there is a very simple result in the Fourier transform, which says that if phi t has the Fourier transform phi cap omega as we do, in general, then phi alpha t has the Fourier transform 1 by mod alpha phi cap omega by alpha for all alpha belonging to the real numbers other than 0. This notation says all real numbers except 0. Of course, alpha can't be 0. So, for example, even if alpha is negative, we can use this. In particular, for example, if alpha is minus 1, we have a reflection of the Fourier transform as well. So, using this, we will now take care of the two so called distortions or modifications that we have made in phi, the translation and the dilation. In fact, the translation does not affect the magnitude. The translation only affects the phase or the angle of the Fourier transform. So, I can even forget about the translation. I need only look at the 2 raised to the power of m term there. So, here if I restrict myself to magnitude only, then phi t has the Fourier transform phi cap omega with a magnitude of mod of this. Phi 2 raised to the power of m t minus n would then have a Fourier transform mod phi cap omega divide by 2 raised to the power of m, of course, with a constant. The same 2 raised to the power of m, but in the denominator here. So, of course, let us take an example. Suppose m is equal to 1 and minus 1 to fix our ideas. And m equal to minus 1. Now, notice that the n is entirely absent here or here. The n is irrelevant as far as the magnitude goes. The n only contributes to the phase. Let us sketch both of these. How would these look? So, let me take the m equal to 1 case. Let me sketch this. So, omega by 2. So, if I focus my attention on the main lobe and the principal side lobes that I have here, this was originally 2 pi, now it has become 4 pi. This was originally 4 pi, now it has become 8 pi, and so too on this side. This is minus 4 pi and so on. So, you have stretched by a factor of 2. Let me put them together, the original Fourier transform and this Fourier transform with m equal to 1. And so on. This is, I am just sketching mod phi cap omega, and here I sketch mod phi cap omega by 2 multiplied by half. Of course, this should be smooth here, all these are smooth. So, as expected, when we squeeze in time, we have stretched in frequency. And now, let us interpret what we are doing when we take a dot product to calculate the coefficients in a V m. To calculate coefficients, in a subspace V m, what are we effectively doing? We are taking an inner product, namely the inner product of an x with phi 2 raised to the power of m t minus n. Remember, now you know there is of course a normalization here. So, if you want to work with an orthonormal basis, then it should not quite be phi 2 raised to the power of m t minus n. One must normalize it to make it unit norm. So, I will take an instance. Let us take any arbitrary m and let us look at the norm. So, if we consider phi 2 raised to the power of m t, and again the minus n does not affect the norm. I am talking about the L2 norm, and therefore, we can as well take without loss of generality we could take n equal to 0. Let us find out the norm therefore. So, I am putting 2 raised to the power of m and then a dot. Dot denotes the argument of the function, but we are treating the function as an entity. So, I do not use the explicit argument here. The norm of this is essentially integral. Now, you know when you go over phi 2 raised to the power of m dot, you are talking about 0 to 2 raised to the power minus m here, 1 squared dt, and that is obviously 2 raised to the power minus m. And therefore, if you want to make this unit norm, then you must divide by, this is of course the square of the norm. So, if you want to make this unit norm, you must divide the function by the square root of this. We must consider 1 by square root of 2 raised to the power minus m times phi 2 raised to the power of m t minus n, and that is easily seen to be 2 raised to the power minus m by 2 phi 2 raised to the power m t minus n. So, this is the unit norm. This is now an orthonormal basis. So, let us make that note. 2 raised to the power minus m by 2 phi 2 raised to the power m t minus n for all integer n is an orthonormal basis for V m. You know what V m means. V m is the mth subspace in the ladder of subspaces that leads to L to R as you go rightwards, and to the trivial subspace with only the 0 element as you go leftwards. So, it is that mth subspace in the ladder, and now we have an orthonormal basis for it. Anyway, now let us interpret what happens when we take the dot product of any function in L to R with an element of this orthonormal basis. So, consider x t belonging to L to R, or if you please x with the argument belonging to L to R, as is the correct way to write it. And then consider the inner product of this x with this orthonormal basis element 2 raised to the power minus m by 2 phi 2 raised to the power m dot minus n. Now, we are going to invoke the Parseval's theorem. You will remember that we had discussed the Parseval's theorem a while ago in one of the earlier lectures, when I had talked about the relationship of functions and vectors. I had mentioned the significance of Parseval's theorem. There are different ways of stating it. Parseval's theorem on one hand says that the inner product is preserved as we go from time to frequency. Now, here if we use angular frequency, a factor of 2 pi is needed. If we use Hertz frequency, that 2 pi factor is not required. But since we are working with angular frequency, it would be safer to retain that factor of 2 pi. But that factor of 2 pi apart, what Parseval's theorem says is that after all, when you go from the function to its Fourier transform, in effect you are representing the same function in a different basis.